So let's welcome Abhijit and give him a big hand.
Thank you, and welcome to Track C, and I'm very happy to see all of you. We're going to discuss in this first section, we're going to discuss deep learning with a focus towards the image applications. And this is near to my heart because I studied image processing when I was in graduate school. So this is where I came from, and now I'm always in this world. It's great to be back in Taiwan. So I want to start with a little bit, well, first of all, before we even start, I want to mention that I have some fabulous prizes here. And these prizes are for if you ask questions. So this is not like the keynote where everyone's quiet. Please raise your hand and ask questions anytime. And sometimes I might ask you a question. And if you answer, you might also get a prize. Who knows? It might be your lucky day. All right? So with that, I have one first question for all of you. Raise your hand and tell me, what does MATLAB mean? MATLAB. It's made up of two words. MATLAB. What does that mean? Yes. Matrix Laboratory. Very good. And for that, you get a hat, sir. So, that might have seemed like an easy question, but we're going to make it rain in here. So, keep them coming. Now, this is an example of a very simple, relatable image classification, AI example. So here we have maybe 5 types of foods, and I want to be able to recognize these objects. And I'm showing how you can do that in MATLAB. Here I have my friend. He is pointing a camera at the different foods. And the one thing I want you to notice is we have trained a model to recognize these foods. And you can see the captions are being created here. Look at the code. Look at how many lines of code there is on the right side. I promise to you, I'm not hiding anything in a function. This is all the lines of code you need to do what I'm doing here, which is access the camera, apply the model, and generate the text that tells you what the food is. So, as I was saying in the earlier keynote session, MATLAB, we're trying to make it easier and more accessible for people to do AI. So with that, there's 3 simple messages I want to give you. And that is, first, MATLAB is productive. And MATLAB, secondly, is fast. Sometimes there is a misconception these days that, MATLAB is kind of slow because it's not compiled. But that's not true at all anymore. We have a lot of performance enhancements, and you'll see some of them as we go through. And the third thing, which is very new to a lot of people, is MATLAB integrates with open source. We're not telling people, uninstall TensorFlow and take MATLAB. We integrate with open source. So there are many applications of deep learning, and you'll hear a lot of them throughout today, and you know many of them. Voice assistants, teaching a character to beat a video game. That's a different type of deep learning, but it's also one of the applications. Automatically colorizing black and white images. Again, remember, think of it as, instead of you writing a program to do something to an input and make it into an output, you are now writing a program that will generate the model, generate the program that will make this decision. So what does deep learning actually mean? Does anyone want to help me define deep learning? Can you give me a definition? It's one of those tricky terms everybody thinks they know. Anybody want to guess? I have t-shirts. All right, let you guys wake up a little bit. Deep learning is learning that is not shallow. No, I'm just kidding. It's a form of machine learning. It's a form of AI where you learn to do something. You learn to perform a task directly from data. And that's different from some of the other AI techniques, different from some of the other machine learning techniques. Because in this case, you're learning directly from the data. You're not teaching the machine what is important about the data, what is not important about the data. That is inferred automatically. So deep learning can encompass many different data types. I'm going to focus for now on images because that's also where the AI field started. But there's a lot of different data types, signals, text, images, and you can imagine many other types of data as well. And deep learning is quite versatile. It can do so many things. And we all saw this example earlier where you are trying to segment. This is called semantic segmentation, where you're trying to identify the outline of key objects like the road or like the cars. Okay, that is one way. That's an algorithm trained specifically to do one thing. Another example on the right is creating a filter that can remove rain. Now imagine how difficult that would be if you have any image processing background. You probably understand how difficult it is to design a filter by hand that can do something that sophisticated. So we are no longer interested in designing those filters by hand. We want to have machines learn those filters for us. And so this paper illustrates that you can remove rain by teaching a machine what it should be when it's not raining. And then lastly, here's another example where you have the ability to recognize a person's iris, which means that you can recognize the person and give them access or deny them access, and so forth. So this is, well, let me ask you this. Raise your hand if you are currently practicing deep learning today. Please raise your hand. Okay, don't be shy. It's just, it's usually only a few people, which I saw, great. And so that's maybe 3 or 4 people in the audience raised their hands. And this is exactly the audience that I love to speak to because many of you are curious. How can I use deep learning? And what can it do for me? Yes, there's a question. Ah, good question. I'm going to repeat the question and give you a t-shirt. How many layers, thank you, how many layers do you need in a network before you can consider it deep? Does anybody want to give me an answer? How many layers is deep? You already got a prize, but you can answer. More than 3. Okay, what's the source for your... more than 3 hidden layers. Okay. Where did you get that number from? Most tutorials. That's what I wanted. I wanted to hear where you got that answer. Yeah. The notion of deep learning, how many layers is deep, is vague. It's more or less a number of hidden layers in the middle. There's not really a consensus. Some people say 3, some people say 5, 7. So if you have a number of layers inside a neural network, it's considered deep. But there's not really a agreed upon standard. So before we get into the neural network architecture and understand the math of it, let's see why is it that deep learning performs so well. As we were just discussing, there is this neural network architecture, right? Deep learning makes use of neural networks. There's an input and there's an output, and then there are multiple hidden layers. And in some cases, there could be multiple inputs and multiple outputs and many different topologies of hidden layers. But we're not going to focus on exactly that right now. Let's think about layers as an abstraction. Imagine that the layers are like Lego blocks. The input of one layer comes from the output of a previous layer. Stacks on top of each other like this. So every hidden layer is processing the information coming from a previous layer. And what are these layers? We'll get into that in a second. But these layers don't have to be just one after another. Sometimes you can split and combine layers, like you see here. Just the analogy of a Lego block. So they can be ordered in different ways, and they do different things depending on how you order these layers. So I have a video here, but I would actually prefer to go right into MATLAB instead of playing the video. So this is MATLAB, and let me make it larger so everybody can see. Okay, so I'm going to do deep learning in only a few lines of code. The slide said 6. Let's see if we can beat that. Okay, so let's say I want to recognize an image. So I have an image here. And let me show you the image. So this is an image of peppers, okay? Also there's other things like garlic, but let's just say that this is mostly, dominantly, it's peppers. Now, how would you use a neural network to recognize what is inside this image? Well, unless there's already a network trained to find peppers, you would have to train it yourself. Luckily, it turns out there are existing neural networks that know what bell peppers look like. So I'm going to use one. There's a famous one called GoogleNet. And so I'm going to go ahead and invoke this network. MATLAB comes with a lot of built-in research networks like GoogleNet and ResNet and AlexNet and many others. But if you have networks that you want to use that are not there, you can import them. So you see, this network here is a data structure containing some 144 layers in it. It's a deep neural network, of course. Now, how do we use it? See, it's an object in MATLAB. And objects in MATLAB allow you to use functions and properties. So if I type net.classify on the image, I should get back an answer, which is the classification of the image. But I don't. I get an error. And this error is meaningful because it says that it has to be something to do with the correct size. So I don't have the correct size. And all I got to do to fix this error is I have to resize the image. So I'm going to try the same command, except I'm going to resize the image. But what size do I want it to be, right? I have to look at what size is acceptable. So if I look at the layers of the network, now look, there are 100 and something layers. But the top layer, which is the input, it has a particular dimension, which is this size. The images must be of a fixed size. And this is the case with all neural networks. Feed-forward neural networks are fixed architecture. That means that the size of the input is always the same. The size of the output is always the same. I'll get into the ramifications of that in a little bit. But anyway, I have to resize the image so it's the correct size. So all I'm going to do is I'm going to resize here using MATLAB's handy-dandy functions. So let's do 224 by 224. And then that's it. There's the answer. MATLAB used deep learning, a deep learning model, to recognize that this is a bell pepper image. So why does it need to be a fixed size? Because, in the real world, real images are not all going to be the same size. Well, that is where you have to do a lot of pre-processing. There is pre-processing required for any AI task. And one of those happens to be resizing, but many other pre-processing steps might need to be taken also. So we will talk about some of those pre-processing steps as well. So let me skip over this and go into how MATLAB makes you productive, especially when it comes to deep learning. Now, yes, there's a question. No problem. Yes. Okay, great question. And for that, you get an umbrella. Here you go. Keep you safe from the rain. So we have, thank you. The question was, the demo I showed you only does inference. What about training? Does MATLAB help you do training? So the answer is, of course, yes. I chose to start with inference because that's simple, everybody understands. Using a model to make a prediction. But of course, to create the model in the first place is the hard part, which I will talk about as well. In fact, I'm about to talk about the structure, how you do that in MATLAB. So great question. All right. Any other questions before I go on? No. Okay. So this is probably, I would say, my most important slide in this presentation. But don't worry about trying to draw it all on your paper. We will provide the slides to you. But this is the key slide because it illustrates how you actually design a system that can do deep learning. And this is, we've seen a variation of this before, but I'm going to repeat this again. You have to have a way to explore and access data. If you can't get data, you are done. You have no, if you can't do that, you're not going to be able to do machine learning. So you have to have some way, some method to access data, whatever framework you choose, right? And then the next part is to somehow label and pre-process the data. Suppose that I want to develop an AI that can recognize cars. Okay, cars are driving, I want to recognize. If I want to create a data set where I have thousands of images of cars, well, that's something I have to go out and do. I could take many hours of videos, but then I have to find the car in every frame of every video. Who wants to do all that work? Like I said earlier, who wants to do all that work? So then the notion of automating labeling is very important. To do any real work in this field, you have to be able to do work automatically instead of all manually. So that's this part of labeling and pre-processing. Another thing is, here's an example I often give, and that is, suppose that you are looking at X-rays, or if you're looking at microscope images of people's cells. You want to know if they have cancer, okay? You want to create an AI that can detect cancer. How many examples are there in the world of healthy patients, and how many examples are there of cancer patients? It's a very imbalanced set, right? Maybe 1,000 healthy to 1 cancer. So in the real world, you will always find that there is imbalance in the data set. And sometimes that means that you have to rebalance the data by either collecting more data of the case that you don't have enough, or you invent more data by generating or augmenting your data set. So the reason I'm focusing so much on these two topics is actually when you are ready to do your real work in machine learning, you are going to spend 80% of your time managing data and pre-processing the data. This is the real world work that nobody likes to do in machine learning. That's why we have to have tools that make it easier. But of course, once you have the data, you can do the sexy part that everybody likes, and that is creating the models, right? The AI model. And you can use GPUs to accelerate your process. You can use tools to monitor your network and tune the hyperparameters. You know, in neural network land, we're very fancy. We don't call them parameters, we call them hyperparameters. So hyperparameter tuning is key. But you know, there's a reason there's a gap at the end, because if you've created your AI, you're not done. Who here has a job where all they're supposed to do is deliver an AI model? Practically no one. You all are here because you have a different deliverable. You have a product. You have a service. That AI needs to be integrated into that product. And so this idea has to be there of integrating a model into a system. Once you have your model, you have to have a way to implement the model. And that may be in an embedded system, that may be in a desktop or enterprise application. Whatever it is, you have to have the path. And this is something that I'm happy to say all of this MATLAB can do. But it's not necessary for you to only use MATLAB. You can say, you could prefer to use something else for one of these pieces, like if you want to use TensorFlow for creating a model, you can do that. But then use MATLAB to make the labeling easier. Use MATLAB to integrate the system with the model. So those are the kinds of things that people are doing. And so there's a famous quote, I love to label and pre-process my data, said by no engineer ever. And that's, of course, the reason we have these automation tools. I'm going to go into a little bit of detail about that now. So there was a customer in the United States, probably many people are familiar with them, Caterpillar. Caterpillar makes construction equipment like this here. And they're the leading manufacturer of construction and mining equipment. Now the problem that they had was they're now developing autonomous vehicles for construction. And these autonomous vehicles need to work in a work area where there are humans and other vehicles, and they need to be able to recognize the objects around them. So that means you have to have examples of people. You have to have examples of other objects. And then you can train a model. So this is a massive labeling task, because nobody in the world, there's no public data set of construction vehicles. There's no public data set of people inside a construction zone. So this is something they had to become experts themselves. And that means that what they started out doing was they were hand labeling objects inside of different images. And this person at Caterpillar, one of the managers, said that they were spending way too much time creating the ground truth data. That's what that means. Ground truth is the human labels. Now, of course that is the case. If you don't have automation, you will spend too much time. And so what they did with our tools is they created a semi-automated labeling process. Instead of having to label 100% of their data, they only had to label 80 or 90%. Now, if you're thinking of millions and millions of data samples, this is a significant amount of time that they saved. But they also use MATLAB for their whole development workflow because that also saved them time. And this is a story that is available on our website if you want to know more details. So how does MATLAB actually help here? So this is something we showed earlier, which is you can use a labeling tool. We have multiple labeling tools. This is one called Image Labeler. So I have a few images that I'm pulling in, and I can start by creating some labels, and then I can draw the boundaries of the different objects. So here I'm creating a vehicle label. And then I'm going to draw the bounding box around the vehicle. It's very simple tool, specifically designed for creating labels. Now, let's say you want to automate this. You know, I have another image that I need to label, but I don't want to do it by hand. There's the automation tool at the top. I know it's small and you can't see it, but we'll show you in more detail later. So this has a number of algorithms, and one of the built-in algorithms was a vehicle detecting algorithm. So we use that. And let's say MATLAB, find all the vehicles, and it found a few. It didn't find all of them. Like I said, it goes from 100% to some less percent. You still have to do manual work, but it's a lot less. So here we just manually add the rest, and then we have our labeling. So there's a way to automate a lot of this work, which means that you can create systems that look like this. If you have that data, you can create a detection algorithm. The thing about AI, and so far today's AI, is very narrowly defined. AI is not actually that smart. It can only do what you teach it to do. So if you wanted to detect cars, you have to give it examples of detecting cars. It's not going to suddenly be able to detect horses unless you teach it to do that. So you need to have that labeled data. Now we saw this before. I think I'm going to skip this because it might be the same. Oh no, this is a little different. So there's another tool that allows you to as I said, you have to teach it this exact task you want it to do. So instead of a rectangular label, now I'm going to use a pixel label. And this is a case where you can specifically create data for semantic segmentation. This is where I'm going to provide the boundary, exact boundary of the object. And I can paint a different class here. I'm going to paint in the bus class. And so there's different tools available for different types of labeling. Then I might want to label the road, and so here it is, I'm labeling the road. And similar to the other case, we can automate this labeling for multiple scenes as well. And that's something you can do by going to the automation area. Now there is no automation algorithm built in for finding cars for the outline, so you can create an algorithm or import one from a different library and bring it into this labeling tool. Any questions? All right, so of course, because we label the data at the pixel level with the outlines, you can then achieve something like this, which we saw earlier, where you're detecting something in the label outline. So this is how MATLAB is productive, or helps you be productive. It helps you automate the tedious workflow that is hard to do. And it's easy to load in data, even if you have to do part of it manually. That's the point. Now, let's move on to another way in which MATLAB helps you do deep learning. And that is because MATLAB is fast. And we're going to talk about performance, both for training a model and for deploying a model. Okay? So what is training? Again, imagine that you are trying to identify the type of food that your camera is seeing. You have to have examples of that type of food. Then you create a neural network, and this neural network doesn't do anything yet. you have to apply the process of training by showing the ground truth samples and applying the neural network training algorithms, such as backpropagation, in order to derive the classifier. And so this training is an involved process. Let's use an example where we're going to train an algorithm to identify objects. So this graphic here represents a convolutional neural network. And for images, those are very useful because they can relate spatial coordinates very well together. That's the reason why CNNs, or convolutional neural networks, are used for images, because they have spatial relevance. Now, in this network, typically you have a number of layers, and then at some point there's a layer called a pooling layer. Pooling layers downsample the image and make them smaller. That has the effect of bringing significant structures out of the image. So eventually you'll have a pooling layer, and then you'll have more convolution layers, and another pooling, and you downsample, 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 and you get back a label. Contrast that with semantic segmentation. Semantic segmentation is an example where your input is an image, and the output is also an image. But the output image is labeled, every pixel is classified to which object it is. So there is a network that upsamples the downsampled network. This is also encoder or decoder structure. You can think of it that way. So this is a complex neural network that has that idea of downsampling an image and doing a classification, and then upsampling it back to the image space so that you can get a result for every pixel. And so I'm going to show you how you might design this algorithm in the code. This should answer hopefully your question about, does MATLAB do training? This is where we're going to train an algorithm. So first, of course, you have to explore and access the data. In this case, I have a data set, and I'm going to show you a little bit about the data. There's a public data set on the web where people have gone through and labeled a video full of objects. So these are still frames, okay? These are still frames from the video containing a number of objects. And these are cars, buses, roads, etc. And then there's another folder where there's a corresponding frame. Somebody has hand-painted every object in every frame, okay? Thank the Lord for that. That must have been difficult. But we have that data set. So this is the famous CamVid data set, if you want to look it up online. And we are loading it into MATLAB in a particular manner. We're using these special data structures. I talked about them before, called data stores. They make it easy to load large amounts of images, or large amounts of signals, or large amounts of text, whatever it is. There's different data stores for those. So you can see by bringing in the data store, it's an object, and we use the read image command, and we can read images from the data store, and here's an example from the data set, right? Now the thing is, why we do this is because today our data may be small. Maybe I can load all the data using a for loop. Okay, that would be the nice, lazy way to do it. But what if you have 3 million images? What if you have 3 billion images? The for loop is no way to read in that much data. That's why we have these data structures. They're scalable. They do not actually read the data until necessary. So what about the pixel label data? We saw how we could read images, normal images. How would you read the pixel classification data? These are the 10 different classes we want to identify. So this is a place where you can use another type of data structure, specifically we created for this. It's called the pixel label data store. And this captures the classification information that you have in the data. And then you can apply it. So this is important because we have to have both the ground truth as well as the data, the image data. And this is, you can see, this is an image where every pixel is categorized as road or lane, and that's the image that came out of it. It's tiny. But you see, that's what you need to be able to train such an algorithm. And this is an example of what the image looks like if you were to overlay the labels on top of the image. So you can see, this is just, again, this is the ground truth. We haven't actually trained the model yet, which is what we're about to do next. How do you train the model? Once you have the data in MATLAB, how do you train the model? So we're going to prepare a neural network first. And this is what it looks like. A neural network must contain a number of hidden layers. It has to have an input, has to have an output. And so we're counting how many inputs we have just to see that there is actually quite an imbalance in the amount of pixels we have for certain categories. You can see that we have way more examples of road pixels versus car pixels. So I predict that this algorithm will be much better at classifying roads than it will be at classifying cars. Let's see though. We can rebalance that somehow. So we will try to rebalance it by pre-processing the data a little bit, because that's going to be a problem otherwise. So at this point, we are now ready to create the network, and there is a function we have specifically for segmentation called segment layers. You can take a neural network that already exists and create a segment out of it. There are also other semantic segmentation networks besides segment, but anyway, we're using that as an example here. The reason we're using that is because we automatically get the nice encoder-decoder structure provided to us by this segment layers command. It's a generator for a neural network. This neural network is not trained. It is not yet trained to do my task, but it is there ready to begin training. So as we move forward, I am now using a little bit of weighting. Class weights here is one of the ways where I will pre-process the data to try to account for the imbalance of the data. So we had too many pixels of road and too few pixels of cars. This is a way that we could try to rebalance it. So this is our neural network. It's not yet ready. One last step is there, and that is we have to replace some of the layers. This is what's called transfer learning. You have to use an existing network, but you got to change it a little bit before you can use it for your new application. So we are taking an existing layer from the neural network, removing it, and adding our own, which is part of what you saw in the code. Now, if I was going too fast and you kind of missed some of it, it's okay. I will provide you this explanation and example that you can study afterwards. We have limited time, so I didn't have enough time to explain all the details. But now we can actually train the network. We are ready. So this is where I'm going to apply the actual training. First, you have to set up your hyperparameters, as we said. This is easily done with MATLAB's training options. And training options allows you to specify all the little properties that will go into the training. And then finally, we're going to, well, I guess one last step. We're going to augment the data to make it a little easier to train for different cases. So I'm randomly rotating some of the data just to make it a little harder for the network and make it better. So I'm going to skip ahead. There it is. Okay. Now the train network command takes your input, which is your data. It takes in your neural network and your options. And then this is how it looks after you train. This actually took 11 hours to train. You didn't know it, but 11 hours just passed, and now we've done. And we have trained a neural network. The last step is once you train it, you got to make sure it works. So let's test it. This is a way to evaluate. Now I'm going to show you something. On the left side, you have the original image by the researcher. They have created, that's the ground truth. But on the right side is the output from your algorithm. Now, look at the two images. You can tell that there's differences. Now, how do you measure if the images are, how do you measure that the model is actually performing well? If you count the number of pixels that are wrong, you may get a very bad result, right? Because there's there's hundreds of pixels that are wrong. But how wrong? I mean, let's say I was creating a self-driving vehicle. On the ground truth, I see 5 people. On the prediction, I see a blob of people. The car will know not to hit the people either way. So this is a case where I'm giving the idea that simply counting the number of correct classifications is not the right way to measure the goodness of this model. You have to have some other metric. And so we provide a few other metrics here. One example is to look at the intersection over union. That is, what is the overall overlap of the correct answer with the predicted answer? And this is the kind of thing that you want to use to evaluate. And then there are other ways You know, there's other metrics as well that might be more meaningful depending on your problem. And so the way to find these metrics is to use there's a command that is going to show up here. Let's skip quickly to the end of the command. Evaluate semantic segmentation. That's another, again, metric that we provide to make this easier. And there are many metrics that come up. You can do intersection over union, you can do a mean accuracy, etc., etc. So there's lots of ways to measure. So we addressed a bunch of challenges: accessing data, labeling preprocessing, using previous research, developing algorithm, evaluating. And so what's next? You can scale deep learning. You can do deep learning on multiple resources. If you want to do it on a machine, typical machine has a GPU or a CPU, it's automatic. But if you want to go to a multi-GPU machine, you can select the multi-GPU option. But if you want to go to a compute cluster, all you got to do is select the parallel option. And you can now do your training on AWS, on Azure, or any other cluster that you might have. So this is a very important retargetability of the training. Training performance is very good in MATLAB. It's comparable to TensorFlow and other frameworks. I'm going to also mention that MATLAB is very fast for deployment because of GPU coder. Now we have a talk later in one of the tracks, I think it's track D, on automatic CUDA code generation. I'll go into detail about that. And so you can see with changing MATLAB into C code or C++ code, you can get a huge performance benefit like you see in this case. We have this demo running outside. One of our great partners, NVIDIA, has this demo running, and they have it running in real time. It's very impressive. You should check it out. So that's the performance benefit you get. And so there's this inference chart. I'm not going to go into detail about all the numbers, except to say that because of GPU coder, MATLAB is oftentimes faster than TensorFlow, MXNet, and even PyTorch, which I'll show on another slide later. And so MATLAB is very comparable in performance to the open source frameworks. So that's one last piece of MATLAB is fast. MATLAB works with open source. And I will say that the way you access the models is through a number of add-ons. These are free add-ons that come with MATLAB. If you have the deep learning toolbox, you can import models from Keras, Caffe, or Onyx. And this is something that we'll also go into more detail in the part 2 session, how you can import models from these different frameworks. So you can also export. That way you can train something in MATLAB and give it to your friend who uses Caffe. I'm not going to go into detail here. This video simply shows how to use a function. I don't think that's useful to see. But you can import models into MATLAB that way. And so Onyx is the open neural network interchange format, and that's why it works with many different frameworks. MATLAB is we are part of the Onyx organization, along with along with Microsoft, Facebook, and Amazon. MathWorks is part of this consortium. So we have input into making sure that these deep learning standards work well together. All right? So I'm not going to go into all these details. There's a lot of benefits to bringing in Onyx models into MATLAB, because then you can use other research in your work. Okay? So I'm going to provide all these slides to you guys. Again, I apologize because of the short time. We don't have time to cover everything in detail. I would have loved to do that, but we know that you're here to learn more. Throughout the day, we'll have much more about this. So there's a whole page about how MATLAB integrates with open source. I'm not going to cover that. And so these are the 3 main benefits to wrap up. These are the 3 main benefits of using MATLAB for deep learning. It's productive, it's fast, and it integrates with open source. Thank you.
Any questions?